students, today in this video I am going to explain about nuclear physics, which is one of the important part in your second year physics plus 2 or intermediate or what you can say. So since it is the introductory class, so definitely I would like to discuss something about the nucleus. I have written nuclei, that means it is the plural form of a nucleus. You know that the central part of the atom is nucleus. Central part of the atom is the nucleus. In Rutherford alpha particle scattering experiment, he revealed that the central part of the atom is positive in charge. In fact, in his experiment, alpha particle experiment, he found that most of the alpha particles passed through the gold foil undeflected. Very few alpha particles passed through the gold foil with appreciable deviation. That means the central part of the atom is positive in charge and it is very small in comparison with the size of the atom. Generally, size of an atom is about 10 to the power minus 15, 10 to the power minus 10 meter. Size of nucleus around 10 to the power minus 15 meter. That means the size of nucleus is 10 to the power 5 times, or you can say the size of the nucleus is 10 to the power 5 times smaller than the size of the atom. So in Rutherford, in his alpha particle scattering experiment, he revealed that the central part of the atom is very small, which is positive in charge. Later, the existence of a proton as well as neutron is established. That means the credit to the discovery of nucleus goes to the Ernest Rutherford. So today in this video, I shall prefer to discuss about the structure of a nucleus, or you can say properties of a nucleus. Structure of a nucleus. So nucleus is the very small portion of the atom. In fact, it is very small that it is not possible to draw a sharp boundary for the nucleus. Just we can assume that it is like a sphere. In fact, the shape of the nucleus depends upon the number of constituents. Its size depends upon the number of constituents. Since it is very small, we assume that it is like a sphere. How the atom is a sphere, inside the atom, which is the nucleus, which is very small, we can assume it like a sphere, but actually the shape of the nucleus or the size of the nucleus vary from atom to atom due to difference in number of nucleons, that means protons and neutrons. So I can say that the particles present inside the nucleus, particles inside nucleus are nucleons, means mainly protons and neutrons. You know that outside the nucleus, what we say, extra nuclear part, electrons are revolving in an orbit around the nucleus. There is a huge space between the nucleus and the outermost electron. Due to that, in Rutherford's experiment, it was found that most of the alpha particle passed through the gold foil undeflected. The fact is that there is a lot of gap between the central part nucleus and the extra nuclear part. So here the nucleus depends upon the protons and neutrons. Protons are positive in charge, neutrons are neutral. So the central nucleus is positive in charge. You know that mass of proton is almost 1836 times than mass of an electron. Mass of proton is about 1836 times of mass of an electron. That means I want to say that the mass of the atom almost equal to mass of its nucleus. The mass of atom almost equal to mass of nucleons present in its nucleus, because the mass of proton and mass of neutron almost equal. Neutron is little more in mass than proton. Then what are the mass of electrons and protons? Already you know that electron is negative in charge, whereas the proton is positive in charge and neutron is neutral. So the charge of an electron, I can write 1.6 into 10 to the power minus 19 coulomb, or if you want you can write 1.602. Okay, this is the mass of an electron, sorry, charge of an electron. So charge of a proton, same charge, 602 into 10 to the power minus 19 coulomb. But this is negative, this is positive one, and the charge of a neutron is 0. That means neutron is neutral in charge. What is the mass of electron? You know that mass of electron is very small in comparison with the mass of a proton. Okay. So first let's write mass of proton. Okay. So mass of proton is equal to 1.6726 into 10 to the power minus 27 kg. Okay, and so far as mass of a neutron is concerned, it is 1.6749 into 10 to the power minus 27 kg. What about the mass of electron? Mass of electron is equal to 9.11, approximately I will take 9.11 into 10 to the power minus 31 kg. This is about the mass of proton, neutron and electrons. Okay, so the mass of proton is about 1836 times mass of an electron, and mass of proton and mass of a neutron, you are observing here, almost equal, but it is neutron is little more than mass of proton. If I express in another unit, it is 1.00866 unified mass. Okay, or if you express this mass of proton in unified mass, it is 1.007273 unified mass, and you know that one unified mass is equal to 1.66 into 10 to the power minus 27 kg. Okay, this is about the mass of electrons, protons and also its charge I have mentioned. You know that in nuclear physics, or I can say in higher energy physics, nuclear physics, or you can say in higher energy physics, we express the mass in energy unit. In nuclear physics, it is customary to use mass in energy units, because according to the theory of relativity, or you can say that mass energy relation, energy is present in a matter in the condensed form, what we say mass. That means mass and energy both are convertible. So according to the mass energy conversion, or you can say E equal to mc square. M is the mass of the particle, suppose electron, suppose m is the mass, E is the energy. That means the mass can be equivalent to energy, because according to the Einstein, according to the theory of relativity, energy is present in matter in the condensed form. That means mass can be converted to energy, or energy can be converted to mass. So I said that in nuclear physics it is customary to use mass in energy units. Mass in energy units. What mass in energy units? You see that. That means we can express the mass in electron volt, in million electron volt or kilo electron volt. These are the units of energy in nuclear physics, no doubt at all. But we can express in nuclear physics, or you can say higher energy physics, the unit of energy as the unit of mass. Now you see that, suppose this is a negative plate, this is a positive plate, okay. Here it is 0 volt, here it is 1 volt, 1 electron is there here. That electron I want to shift it from here to here, from A to B, you can say from A to B. How much energy it required? That is equal to 1 electron volt. Listen carefully. This is the negative plate, this is the positive plate, an electron is there. I want to take it from here to here. It needs some energy. I have to do some work. That work or that energy it required to move from 0 volt to 1 volt, that is equal to 1 electron volt. You know that this potential energy is the product of a charge and potential difference. You know the charge of an electron 1.6 into 10 to the power minus 19 coulomb, and in place of potential difference I can write this is 1 joule per 1 coulomb, because potential difference is work done per unit charge. Work done is joule, charge is coulomb. Work done per unit charge is the potential difference. So if 1.6 into 10 to the minus 19 coulomb, this coulomb cancel, so I can write this is 1.6 into 10 to the power minus 19 joule. Okay, that is equal to 1 electron volt. So 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. So I said that in nuclear physics we express the mass in energy form. For example, you see, I want to convert mass of an electron into its equivalent energy. So definitely I shall take the help of the formula E equal to mc square. E stands for the energy, E stands for energy, m stands for mass, c stands for velocity of light. So I can write E equal to mc square. So m is the mass of an electron. I want to convert mass of an electron into its equivalent energy. So E equal to mc square. So I can write 9.1 into 10 to the power minus 31. This is the mass of an electron. Speed of an electron is 3 into 10 to the power 8 meter per second. So I can express this mc square. If I calculate, I shall find that this is 81.9 into 10 to the power minus 15 joule. So if I want to convert into units of energy, either kilo electron volt or million electron volt. Suppose I want to convert this into million electron volt. So 81.9 into 10 to the power minus 15, I shall divide with 1.6 into 10 to the power minus 13. I want to convert this joule into million electron volt. So the answer will be 0.512 million electron volt. That means the mass can be converted into energy. So if this is the matter, then I can say that the M will be equal to 512 million electron volt per c square. See that how the mass is expressed in the form of in the unit of energy. So this is about the mass of the electron. So you can write mass of the electron, no problem. Similarly, we can express the mass of the proton also in this form. It will be 931.2723 million electron volt per coulomb square. If it is the mass of the neutron, then it will be equal to 939.563 million electron volt per coulomb square. So the mass can be equivalent to energy. Except this unit, already one more unit I hope that you know, that is the unified mass. What we have been using in lower classes also, that is unified mass unit. That shortly we represent it in the form of U. So U means unified mass unit. Okay. So what is that? This is 1/12 of a mass of a neutral carbon atom. This is 1/12 of mass of a neutral carbon atom. Neutral carbon atom means which contains 6 number of electrons as well as 6 number of protons. So one unified mass is equal to 931.478 million electron volt per coulomb square. I can express this unified mass also in energy form. Okay. So this is about the units of protons and neutrons. Why I am giving stress on protons and neutrons? Our topic is nuclei. That means we are going to discuss more details about the nucleus. Those are the constituent of a nucleus. Generally, a nucleus we represent like this form. See here. This is the Z, this is the A. So Z stands for number of protons, means atomic number. Atomic number. A stands for mass number, means number of protons plus neutrons. For example, you see that helium. I am writing the atomic number 2, mass number 4. We can also write like this. So this is for proton atomic number, this is for mass number. You know that number of proton plus number of neutron, that is equal to mass number. A equal to Z plus N. So here if I want to find the neutron, so I can write that this neutron, generally write small, is equal to 4 minus 2, that means 2. Here 2 protons, 2 neutrons, the total mass number is 4. Listen carefully, mass number and mass little different. When you say mass, we also consider the electrons. But since the mass of electrons are negligible, we prefer to use most of the cases mass numbers for conveniency, which represents number of protons and number of neutrons. So in this topic you will come across one more important term, maybe, that is nuclei. So what is the nuclei? The nuclei is the nucleus of atom. It is nucleus of atom of specific isotope. Specific isotope. That means given Z and N. Listen carefully. You know that isotopes, atoms of the same element but different mass, are called isotopes. For example, hydrogen, its mass is 1. Deuterium, देखो, so its atomic number 1, mass 2. Tritium, its mass is 3, atomic number 1. So protium, deuterium, tritium, these are the isotopes of hydrogen. All atomic number 1, but mass number is different. That mass number is different. That is due to difference in number of neutrons. So we say them as the isotopes. So a particular isotopes are called nuclides. All nuclides are not stable. About 1000 nuclides are there, but only 300 nuclides are stable. Stable in the sense they do not emit the radiations. But those nuclides are unstable, they emit the radiations. As a result, their constitution comes under change. So in this topic, we will study mostly about the unstable nucleus. That means those nucleus after radiation changes its constitution. So in this topic, in the upcoming class, I shall explain about some other properties of a nucleus. Until then, bye.